Okay, recording is rolling. Today is Monday, August 22nd. I have a lab lined up for you guys today. Before I dive too far into that, tell you guys what we're doing next few days and do some follow up last week. So we're now getting into linear motion proper. So some of the pages that I'm going to give you guys pretty soon, but I don't want you guys just focus on the lab right now. But if you want to get a sneak preview, some of these documents are already in Google Classroom. See, we're going to be looking at linear motion, like motion in a straight line. So you guys see this car like rolling down the incline. Do you guys think this car is like speeding up as it's rolling down? And I wonder what all different scenarios you could have that involve just linear motion. Just think moving in a straight line, possibly forward, maybe forward, backward, down, up and down, take a ball, throw a shape in the air. And one of the pictures I'm going to give you guys looks like this and involves every single possible linear motion scenario that you could possibly have. So there's like, 10 of them. They're spelled out here. So like this one, a ball is thrown straight down with some given initial velocity from the top of a cliff. Ooh, on Mars, hey, where the gravity might be different. Hits the ground some given kind of velocity, so you get the speed. Hey, I wonder how much time to reach the ground and what's the height of the cliff, right? So something like that, right? Lots of scenarios there. On the other side is a bunch of conceptual questions that if you guys have really good graph, really good understanding of this, then you should be able to get these. But see, one of these says if you throw something upwards, then what's the direction of the velocity, what's the direction of the acceleration, so like that. And so I've got those printed out, give those to you guys. I've also got you guys your college physics linear motion homework. We're going to solve a bunch of these. Actually, we might end up solving more of these than we normally do because today's a 3-hour block class day, and also tomorrow is going to be a 3-hour block class day. So I will get you guys plenty well ahead of my other classes, and then we can actually use the little spare time that we have to do more like free response questions. Got some kinematic questions there. Okay, so it's a little peek ahead next couple of weeks. Okay. Also from last week, you guys remember I sent you guys home with this question. This isn't anything in grading for homework, but this is a challenge question. I forgot. Let me pull it out of this plastic sleeve so it's not all shiny. Trying to cover the answer though. Okay, so we did some dimensional analysis back on Friday. You guys remember that? So if you have a number of say variables that have units attached to them, and you're given some question, if you know how to manipulate units, so let's see if I have a distance and a time. I know if I divide distance by time, that gives me some kind of speed unit. Hey, that might have something to do with speed, right? So, something like that. Sometimes you can find some answer just because you know how to multiply and divide units, so you get the unit that you're looking for. So I gave you guys a real good challenge question here. How much land area would be needed to meet energy demand with just solar? Here's the energy demand of the United States, 25,000 terawatt hours per year. I told you guys tera is 10 to the power 12. Well, you might want to know how bright is the sun shining. I gave you guys two values on that. A maximum value, like it was 12 o'clock noon, all sunny, and then an average value, day, night, cloudy, sunny, everything just kind of averaged all together. And one last number I gave you guys was the efficiency of solar panels. So yes, some energy is going to land on the solar panel, but how much can actually be converted into useful energy? 20% is a pretty good number. Some solar panels like 22 point something percent. So you can round about 20%. Okay, so did anybody go home and solve this? Anybody think they know how much land area it would take? Yeah, what do you do? Ooh. Yeah. Let's see. Now you did square meters. You know what I don't have on this paper right here is 1,000 meters is 1 kilometer. I was gonna have you guys convert that too. You know what? I've got an answer I'm looking at that's in square kilometers. So we'll take a look at that. Did anybody else take a stab at this? Oh, yeah. What'd you get, Connor?
Not 1,251.
Okay. Yeah, it have to be some kind of like a square kilometer, so like some kind of area, right? Okay. Oh, right. So here's how I solve this thing. Start off with the given value. I remember what else I wanted to mention. I said this back on Friday too. This is the back of envelope calculation. So yeah, we're ignoring some things like some engineering problems like, well, how do you store this? Blah, blah, right? But like intermittency. But that aside, so you got 25,000 terawatt hours per year. Now the tera is 10 to the 12, so cancel out tera, got 10 to the 12. Now somehow at the end of the day, I need some kind of square meters, square kilometers. That's what I'm gonna get, right? So look at this 400 watt per square meter, saying, hey, that's how you get the area, right? Square meters. So put the 400 watts on the bottom. Right? Remember the theory of why this works. If 400 watts is sort of like equivalent to 1 square meter, right? Watt, by the way, we haven't even talked about this yet, but even if you don't know what 1 watt is, just dimensional analysis, you can set it up to cancel out, okay? But what 1 watt is, 1 watt, you guys ever look on a light bulb says like 20 watts, 40 watts, 100 watts, right? That tells you the rate that's pulling energy off the grid. So 1 watt is 1 joule per second, which is a rate of energy. Because the sun is constantly shining, right? There's some rate of energy it's delivering, right? Okay, so we got the watts canceled. We got our square meters. Great. Now, if you're talking about square meters, I mean, if you just look on the floor, approximately 9 tiles, 3 by 3. That's a little bit short of a square meter. That's a really tiny land area. So I'm going to convert to square kilometers. Here's one way to do it: 1,000 meters, 1,000 meters, kilometer. Can that convert square meters to square kilometers? Right. So if 1,000 meters are in 1 kilometer, then you could say 1,000,000 square meters are in 1 square kilometer, right? 1,000 by 1,000. Okay. Okay, so at this point we have square kilometers, but there's actually 2 time units we have to reconcile. We got these terawatt hours per year, right? Now, if you ever get an electricity bill one day, it'll probably be reported in some kilowatt hours. You guys know kilo is factor of 1,000, but what's the deal with watt hours? Right? Well, I just told you guys a couple minutes back that watt is like joule per second. Hey, that's like energy per time. Hey, if you have energy per time multiplied by hours, like a time unit, wouldn't that bring you back to like just a solid energy unit? Okay, and then okay, so we got energy per time again. Right? Hours and years. If we can somehow reconcile hours and years, right, they want to be divided. They're both time units. Right? It's a real weird way to express energy, but it's just the way it's done. Right, so I know 24 hours in a day, 365 days in a year. Now the days cancel. This hours cancels with that hours. This year's with this year's. And so at that point, now I do have square kilometers. But one last thing is, what about this efficiency factor? Now, if solar panels are 20% efficient, the last steps you want to do you want to multiply or divide by 20%? And 20%, same thing as 0.20, right?
Well, the amount you need would be multiplied by 5.
There you go. Yeah, you need to multiply by 5 effectively, right? Because if you have an efficiency that's less than 100%, that means you need even more solar panels than had they been 100% efficient. See, if they were 100% efficient, you could just end the problem right there. The fact that they're less than 100% efficient, you need even more. So how do you do that? Well, you have to divide by 0.2. Won't that blow up your number even bigger? Right? Divide by 0.2, same thing as multiply by 5. There you go. Okay. Right, so it comes out to, well, this number, which is approximately the land area of Maine. There you go. So a challenge problem right there. Put that aside. All right. Let's look at what we're actually getting at today. So linear motion. I want to kick you guys off with the lab. All right, so we got this Hot Wheels car rolling down this incline. Okay. I should have a Hot Wheels car up here for demonstration, but you guys get it. Back in the lab area. You guys got lots of Hot Wheels cars. There are lots of inclines set up. I wonder what is the relationship, say among all these variables: the mass of the car, how far it goes, displacement x, the speed of the car, maybe at different after it's rolled different distances or different times. But you guys remember last week I was showing you this new tool we have right here. It's pop that up right here. Right, the car rolls through it, and it will measure its speed, right, because it has a couple of sensors over a very short distance. That distance by time, get the speed. Hey, how much time it's been rolling for? Maybe. Right, you guys got your cell phones today? Okay. Right. Ooh, glad you guys remember to bring those. So you've got stopwatches. And I did prop them all up at the same angle. I did want you guys to either measure or calculate the angle yourself. I did it both with an inverse sine, say like how many books did I stack up here versus how long is this incline? Hey, relative to this angle, opposite hypotenuse. That's some kind of inverse sine relationship you can use to calculate this angle. You can also use one of those protractors that's on your desk. Hmm. Okay, all right. So you can grab that desk for today. Yeah. AP student today. Okay. You guys want me to spoil the angle that I got, or do you want to just go in blind and figure out for yourselves? Spoil it. Okay. Now I do want you guys to do it yourself and see if you got what I got. I got a little bit less than 5 degrees, like 4.7, 4.8 degrees, something like that, both by doing the inverse sine calculation and also by propping up the protractor. So if you round it to about 5 degrees. Okay. So let's leave that controlled for everybody, so we can get kind of compare different groups lab data. I mean, you will have different individual cars, maybe their wheels spin a little bit differently. So, right. But that's what we're gonna do here. All right. Now let's. How do you tackle? I mean, that's a lot of variables to juggle. I know we're gonna keep that angle constant, but that aside, that's a lot of variables to juggle. Ideally, in an experiment, you want how many independent variables that you're actually changing? Just one at a time, right? Okay. And then maybe you'll control for a bunch of things, and then you'll have a dependent variable. So we're gonna do 4 different labs, or I'm gonna split you guys up. You're gonna do 1 lab per group, and then we'll come together and we'll aggregate all the data. Okay. So do you guys see a card on your desk? You guys see a card? Okay. Now, some of you guys have a spade, some of you guys have a diamond, some of you guys have a heart, and some of you guys have a club. Okay, you guys found the card? All right. So depending on which card you have, well, I'm assigning one of these 4 to you guys. Okay. So you guys have some paper out, right? So start copying down whichever table I'm assigning to you. I'll walk you guys through what I'm gonna have you guys do. Okay. So if you have the spade, I'm gonna have you guys try different masses as the function of time. Now there are some scales. Oh, I did get told the triple beam balance. So triple beam balance is back there. The digital scales are back there. Now this is the only one I'm gonna have you change out the mass of the car. I'll tell you what, each car is a little over 30 grams. Now you should like measure the mass of the car, and then you have some lab weights. Can you guys probably take some of that? Do you take some masking tape and tape this to a car? Right? Think you can do that? Just change the mass of the car, but only if you have the spade, right? Okay. Now, I guess if you want to, what would work close enough is if you assume the car is about 30 grams and you add anything to it, like this one's 200, so 200 plus 30 about 230. That's if the scales aren't working for whatever reason, so they should work, right? Okay. So you got different trials. Now, distance. Guys, do you want to change your distance if you're also changing the mass of the car? No. So would this column be controlled? This is going to be controlled, isn't it? Right? But only if you're doing this lab. Okay. You change out the mass of the car, that's your independent variable. And time. Do you think time is sort of like you can think of it kind of like the dependent variable, right? For some set distance. Okay, so suppose the distance is like 200 centimeters over and over and over, or 2 meters, right? I'm gonna put centimeters here, later put meters. Either one you do, the graph's gonna work out okay. So it's up to you. If you want to measure centimeters, you want to measure meters. Okay. Okay. Now, let me tell you guys this. Oh, oops, forgot I gotta connect this device. I'm gonna switch my screen over, see if this connects. Okay, it's connected. So I want to point something out to you guys. Let's see, present screen 2. All right. And that's that. No, this is something that AP always counts a point for. Guys, do you think there's going to be some error in measuring like how much time it takes the car to roll down? Do you think, look how this table is exactly set up. Do you think if you do 3 trials, or hold on, that's not the lab, you guys. Okay, I'm going over this one right now. You guys think if you do 3 trials and then take an average, that you can get rid of some of the error, some of the random error of like sometimes you're a little early, sometimes you might be a little late. Okay, so like doing 3 and take an average is a pretty good practice. Okay, guys got that? You know what? Maybe maybe I'll just show you guys the rest of the tables on the screen. Let me zoom in a little bit. Right. Okay, so that's if you have no, but you guys have different tables. I'm gonna switch back so you guys can see whatever table you're looking at. Right. Switch back over. Okay. If you have the diamond, I'm gonna have you measure displacement versus time, or you can say distance versus time. In this case, displacement distance would be the same value because the car is just going forward in a straight line. Okay, so do you want the mass to change for this experiment? No, now the mass is going to be made controlled. So you just need one value way down. Okay. Now you want different distances that you're letting the car roll. Okay. And you're gonna measure how much time does it take? Click, start, stop. So how long does it take to roll 100 centimeters? How long does it take to roll 150 centimeters? How long does it take to roll 200 centimeters? Okay, how much time? Maybe do 3 times and take an average, something like that. Okay. Now I'm going to throw on one more column that's going to help us out later. Might not make 100% sense why you'd be doing this now, but it'll make sense after this lab is over. I'm going to have you guys square that time. Square, each average time. Do 3, take an average, okay, then square that time. Okay, so that'll be one extra column. Okay. All right, if you have the heart card, I'm going to have you measure what is the speed versus time, right? Velocity versus time. So you're going to also control the mass of the car. So mass is just, you can just use a blank car over and over. And you guys are going to be using these speed sensors, right? Speed sensors, okay. And then take an average, right? If you have the clubs, I'm gonna have you guys measure. Now this one's gonna be maybe like the weirdest one, but yeah, we'll see how it plots out, right? And kind of know ahead of time what this is supposed to be looking like. So measure different distances that the car could roll, and then how fast it's going through the speed sensor, and then I want you guys to do one more thing, which is to square those speeds. That'll help you out later. Okay. All right, you guys have the table copied down at meeting? Okay. Now there's before you guys go back there, there's something else I need to. All right, you guys got your tables. So you guys still copying down. Remember, whatever lab group you're in, you only need one of these tables, right? Whichever one that matches the card on your desk. Okay, the other thing we're gonna have you guys do, actually a couple more things. Right, so one thing is the table. So whichever card you have, you're gonna make the table, collect all the data. Okay. Later on, I'm gonna have you guys make some graphs, 1 or 2 graphs, depending on which table you have. And I have an Excel page pre-programmed, so I'll put in the numbers, and we can make those graphs later to put them together as a class. Okay. Another thing I'm gonna have you guys do though is to do an AP write-up for this. Okay? So there's a specific format that AP always has you guys do with lab write-ups. There's always an FRQ they ask, and there's always a very specific process they go through. Okay? It's these 5 things right here. Okay? This is always AP's approach. So do a number of these, and then students always score really well on this part of the exam, just because I always have them do this. Okay? So what question are you trying to answer? Okay. And here there's 4 questions floating around. Right? This relationship, this relationship, this relationship, this relationship. So you're asking one of those, right? Whichever one you have. Okay. You need to list your measuring tools. Okay? We went through a whole list of those back on last week. So think about what tools do you have? What tools are you measuring? Are you using a stopwatch? Are you using a scale? Are you using a meter stick? Are you using one of these speed sensors? Which AP, their term for it is motion detector. So if you want to be safe, you can call it that. Okay. Then they always, this is just, you're going to be asked this in some FRQ in May. They're going to say, write a data gathering procedure. And what they always want you to do is to use that list of tools and say like step by step, what did you do? So if you mentioned the scale, just have something, oh, I use the scale to measure the mass of the car. Did you use a meter stick? Oh, use the meter stick to measure the rolling distance. Did you use a stopwatch? Oh, time how long it takes to, right? So if you use 3 measuring tools, then just have a point for each measuring tool. I use this tool to measure this quantity. Okay. That's not too bad, right? Okay. Then there's going to be an analysis step. Now, this one, maybe I won't give away exactly right now what each of you guys are going to make some graphs, right? There's going to be 1 or 2 graphs per each one of these setups. Okay? So what should those graphs look like? Right. And then your conclusion is going to be some kind of equation or some kind of relationship. Like you might say, maybe you think that the speed is going to be directly proportional to this time. Like if it's been rolling for twice as long, maybe you think it should be pick up to twice the speed. Okay? Or maybe you think there's going to be like some kind of parabolic relationship. Like maybe you have to square the time to see how maybe that's the square of the time is proportional to the distance it's rolled, for example. Okay? Maybe something like that. Okay. All right. So write up a procedure, and then after you guys gather the data and we put together the graphs and see if you guys come up with the equation, we'll go back through the procedure that you guys wrote up, and I'll have you score yourselves according to what looks pretty close to an AP rubric. So I wrote up 1 for each one over the weekend. Okay. Oh, you know what? I used to give students a page like this. This is on Google Classroom too, if you want it. Okay. It's just that 5-part thing. It's a question, measuring tools, data gathering procedure, how to analyze data, what property of graph would be looking for on which set of axes, and then conclusion, the answer to your question, which oftentimes is an equation or proportionality. Okay. Okay. So I know it's a lot of different things. Okay. Who has any questions right now? Any questions right now? All right. Okay. But I guess we got space for one of these up here. Let me do a quick poll. Well, maybe I'll switch both of these throughout the lab. Okay. I'll leave this one up for now, and then all right, get you guys going on that lab. All right, so let me go ahead and stop this recording.